after this. Somebody was, apart from Prof, somebody was saying that there is, you have question concerning yesterday. So who was talking? Apart from Prof, somebody who wanted to talk. I thought somebody wanted to talk, okay? There's no. Go to this business. Yeah, but Prof, you raised one issue. You say that since you say we are giving impression that logistic regression will take care of fragmentation. Is there a need? And there's nothing that there's no need, because even though you know, for historical reason and sometimes for explanation, you will see. I'm trying to prepare material for us to, you know, we were able to do the meta-analysis. And if you remember meta-analysis, or by the time you get there, that particular thing you did, you know, when we're talking of weighted maintenance, you meet it in meta-analysis. So I ask you, even the knowledge you have gained for the stratified analysis, when you want to do meta-analysis, it will help you. You know, somehow, knowledge is not in isolation. If you have knowledge of something, it may help you in understanding another thing. So somehow, but you will see that no, people don't say they are doing effect motivation, because most of the time we have more than one factors that you want to consider, not just only one. If it's only one, you can really do better. When you have many factors, and you can still do better, it will be cumbersome. It is easier to run multiple regression. Once it is easier to run multiple regression, why should you want to be gathering too many factors? So that is just it.
One by one.
Yes, because it is easier to do it with the approach of logistic regression. Is easier and it's more straightforward. It's more encompassing. So why do you bother yourself now using the other one? So that is why it's giving way to, just like the way ANOVA is giving way to linear regression. It's the same thing that this one is giving way to logistic regression. So I think we can start business of today. I want to quickly, let's start discussing logistic regression. So, you know, some of the knowledge we learn from measures of association, even from stratified analysis with the, all of them will be useful. Even from linear regression, all of them will be useful for our understanding of logistic regression, because it's a little bit complex to understand more than the linear regression. But once you understand it, but the easiest thing is that the funnest thing that the result, the output is easier to interpret than linear regression. You see that people are familiar, odd ratio. Once you just know odd ratio confidence, that what does it mean? You know it, finished. But look at linear regression, you'll be talking of Haru square, all those things. So even many people are still finding it difficult to understand coefficient of determination. And moreover, in medical literature, the logistic regression is commoner than linear regression. So you see that it has come to stay, and you need to understand it. And it's not difficult actually to understand, it's just the basis. And because I like to start from basic principle for people to come from first principle, so that people will appreciate it. Even if you don't even run it, you understand it, it sticks when you understand something from. And that is why I try to go to town to look for simpler way to address it. But however, if you still find it difficult to understand something better, once you understand the final output, how to click and run it, and how to interpret it, it's the same thing. The odd ratio confidence interval, that is the output. But how does it come is what we want to be discussing. If it is just the output, it doesn't even take us more than 1 or 2 hours. We just run and say, this is odd ratio. But it's good to have some background knowledge, because somehow it helps in interpretation. Now, this logistic regression I want to look at is somebody talking, somebody asks question. There's somebody talking. If you ask your question, you can ask, no problem. You can raise hand and ask your question. It's a motivated method for modeling the relationship between multiple dependent variables and a categorical dependent variable. So logistic regression analysis studies the association between a categorical dependent variable and a set of independent explanatory variables. So we have said it many times, regression, logistic regression, linear regression. You know, when we discuss linear regression, we talk about the word regression came from, it's an historical word. Regressors mean to go back. So what does it mean? You move from the from effect to the cause. Say this is okay. Like the example we used yesterday, these people are having cardiovascular disease. What are the causes? What are the things that respond? So you are looking, these people have cardiovascular disease. You look back. What are the things they were exposed to? What were the factors these people were exposed to that made them to have cardiovascular disease? You are looking back from the effect to the cause. What is causing it? That is all the regression is all about. Going back. And I've said it many times that the outcome variable is only one. So per time you are predicting. Like for this one now, you have cardiovascular disease, yes, no. Now, you cannot study more than that one outcome. So, but you can have many factors, you may try to study many factors that may influence this cardiovascular disease. And it makes sense to study many factors because even if your hypothesis come out to say, oh, you want to study the effect of obesity on cardiovascular disease. If care is not taken, if you don't include many other factors, you may not be able to quantify. You may even think, okay, obesity is the most important. It may not be the most important thing. So at the end of the day, if you study other factors, yes, you want to know the effect of obesity on heart disease. But it's good to go to town to collect data about every other thing that may contribute to heart disease. So it will help you appreciate two things. It will help you appreciate the relative importance of obesity in causing heart disease. Is it the most important? Is it the number 2 important? Is it number 3 important? So you want to know. Then effect on other, because some other factor that may be responsible, we talked about confounding yesterday, some other factor that may be responsible for this cardiovascular disease, they may be related to obesity also. In that case, apart from obesity, those other factors contribute. So if you don't study those other factors, it may mask the effect of obesity, or it may amplify it or reduce it. You may be having impression that obesity is the one causing it, but whereas those other ones, they are the one, because they are related to obesity also, they are contributing more. It's not just only obesity. Even sometimes it may even mask the effect of obesity. That a particular thing may mask the obesity. So those are confounding you want to remove. The effect modification, you cannot remove it. What it makes you to be able to separate, okay, if I want to explain the effect of obesity on this thing, we have to explain it separately for the people that are for male and female. You know, because the way obesity works, male and female may be different. Yes, a size may not be a confounder. It may be a effect modification. So you know that the factor that will make a woman to be obese, it may be different from factor that make man to be obese. So those are the things. So when you are doing regression, what it does for you, you have only one outcome variable. It gives you opportunity to study pari super type, the effect of many other variables on those outcome variable to really know the relative importance of each of those exposure variable on the outcome variable. So now, if you are dealing with only one, you can look at the relationship between outcome variable and one exposure variable. That will be simple. And what makes logistic is that the outcome variable is categorical. When we say categorical variable, it's different category, can be 2 categories, 3 categories, 4 categories, 5 categories, but it's categorical. Now it's something like male and female, socioeconomic class, upper, middle, lower. Think of many things that is not number, it's not continuous. But for linear regression, the outcome is continuous. For logistic regression, the exposure is categorical. But one thing is for linear regression and for logistic regression, even though what differentiates them is the type of outcome, the exposure is the same. For linear regression, you can have categorical exposure, you can have quantitative exposure. The same thing for logistic regression, you can have categorical exposure, you can have quantitative exposure. So what makes linear and logistic differ is the type of outcome. So the logistic regression now that we are talking of, if it is the outcome we are talking of, if the outcome, there are only 2 categories, the value of the outcome. Like for example now, if you are studying outcome, socioeconomic status as outcome, and the category is high or low, that is binary. There are only 2 possible. You either belong to high class or low class. That is 2. That is binary or binomial. Binary or binomial. Like the example of a cardiovascular disease we are looking at is either you have the disease or no, or not. That's binary, binomial. But if there are more than 2 categories, like for example, socioeconomic status, say upper, middle, lower. In that case, you have more than 2 categories of that. Only one outcome is and one outcome. Then you can assume any of the 3 categories or 4. Once the value you can assume is more than 2, it will be multinomial regression. Now, that multinomial also, if that particular, those 3 or 4 categories, they are in order, like the socioeconomic status is ordinal variable, because you know the high is higher than middle is higher than lower. That would be ordinal. It's a form of multinomial that is ordinal because there is order. So, you know, there are some categorical variables that they are not in order. They are not in order. So, like, well, if you say marital status, yes, marital status can be an outcome variable for some, because there are some factors that may be responsible for, you know, marital your status. Either you are married or single or you are divorced at a particular age. There are many factors that may be responsible. Like married, divorce, single, all those things, there is no ordinal. It's just nominal because there is no one that say, married is the highest, followed by separated, followed by divorce. No, there is nothing like that, just different category. Just like the way our ethnicity, outside Igbo, Yoruba, other. There's no, if they put Abia as number 1 in the, because of alphabetical order, there's nothing that makes Abia to be number 1 and makes Zamfara to be the last one, because Zamfara is Z. That is why when they are listing the state. So there are some variables that are just nominal, that you just belong, there's no order. Those type of variables, if they are outcome variable, they are more than 2, is multinomial. If you want to do regression, but if it is order, you can do multinomial, you can do ordinal. Then there's another one called conditional. Conditional is used in whenever there are pair, you have pair match group, like in match case control. You know, because that matching really affect the data set, so it's conditioned on the, because when you match, you pair them. So one group is a mirror image of the other group in some particular exposure variable. In that case, it's conditional. So you use conditional logistic regression. But whenever people say logistic regression, 99% of the time is binomial. It is binary logistic regression. That's what we'll be looking at. So, and common things occur commonly. So it's on few occasions that you even encounter this or that one. Even when something, there are many categories. People have a way of dividing them into 2. Somebody asked a question. Somebody was saying hello. Is there any question? So even continuous variable, there's a way we categorize it to make it 2. Like blood sugar. You remember? I said it that time. Blood sugar. You measure people's blood sugar. And I say blood sugar greater than or equal to 126 is diabetic. Anything less is not diabetic. Obesity, BMI above this is obese. The other one not obese. Like this obese and obese, I don't live. It's the BMI they used to do it because the underlying factor, there's a continuous variable set. But it just divides it to 2. See, just like the age we did yesterday also, 50 years and above and less than 50 years. That is you dichotomize. You just dichotomize a continuous variable. Sometimes also it may be many categories or categorical variables. You can just split them. It's just like if you want to know a proportion of a particular, maybe in a place, okay, you say in Lagos, what is the proportion of the Igbos in Lagos? Usually they are not the only ethnic group there. They just want to compare what is the proportion. That shows that you have Igbo, the percentage, the other will be another percentage. It's binomial. So you have divided into, or you want to know the proportion of Ishekiri is there. You just say Ishekiri to another. So it has become binomial. So that is how it works. So that is why everything that is categorical can actually follow that binomial. It's just a matter of collapsing the group and make it two groups. Now, this logistic regression is in a class of what we call generalized linear model. I think I explained there was a time that Prof asked this question. I tried to differentiate between generalized linear model and general linear model. The difference is this. The general linear model is just talking about the model for predicting the value of continuous variable. So, and we have that type of model in many, like linear regression, ANOVA. Those ones, they are under general linear model. The reason is very simple, because the outcome is continuous. It follow that linear rule. So naturally, that is why general linear model. But there are some models like this categorical variable now, logistic regression or Poisson regression that are errate. They don't actually follow line. They don't follow linear model. For you to adapt it, you have to now transform that data set. You transform that particular thing that doesn't follow normal distribution. It does not follow linear model. You transform and now bring a link. Thank you. What you use to transform is the link function. So like you're going to see now, there's a link function that will make the logistic regression to behave as if it's a continuous variable. So all those ones that normally they are not under general linear model, they need link function to follow that linear model. They now classify them under generalized linear model. In generalized, it's not separate class for them anyway. It's an expansion. Even those ANOVA, they are under the generalized linear model. It's an expansion. Let's expand it so that they will be part of us. We're now going to generalize. So when they say generalize, all those ANOVA linear regression, they are under, even though they are the one under general linear model, they are also under it. But they say generalize to accommodate something like logistic, Poisson, survivor, and cost proportional hazard regression, all those ones that normally they don't follow straight line. Now, because there's a need for a link function for them to join. And that's a generalize. That's where the word generalizing that comes in. So I think they will move forward. And let me emphasize this. We have already know that logistic regression is when the outcome is categorical. Now, when we already said that the outcome is usually one variable, but the variable, the possible value of the variable, since it's categorical, I can assume 2 or 3 or more. So when it is 2 category, it's binomial, binary. When it is more than 2, multinomial. If the multinomial is order, it's ordinal. So now, you may be predicting that one variable from only one expression. Sorry, it just went out of it. So, if it is only one exposure, that will be simple regression. Simple. But the word simple is used for logistic and linear, so it doesn't matter. Whenever the exposure, we have already known the outcome is only one variable for all regression. But if it is one exposure, is simple regression. I don't know why it is not single regression, but the nomenclature is simple if it is only one predictor. If you have more than one predictor, is multiple regression. I don't know why it is not complex. Since that one is simple, why is it not complex? And if they say this was multiple, why is that one not single? That's just it. That is the caution. So we have simple logistic regression, multiple logistic regression. You have simple linear regression, multiple linear regression. So it is the multiple you call multivariable analysis. Multiple regression, multivariable. So when you are talking about multivariable, it may be logistic, it may be linear. So multivariable means multiple regression. It's not multivariate. That is not multivariate. It's a misnomer, because if you do, many people call it multivariate anyway. If you go and see standard statistic textbook, not all those small ones. Standard one, you see multivariable. And the one under multivariate is those one, apart from the fact that the exposure are many, the outcome also are many. Predict 2 outcomes. Just like now, you may predict both systolic and diastolic blood pressure at the same time from exposure predictor using maneuver, which is multivariate analysis of variance. So that is a form of multivariate analysis because you are predicting more than one outcome variable at the same time. That's the one that is under multivariate analysis, like maneuver, like multi-dimensional scaling, like factor analysis. Those are the ones that fall under multivariate analysis. Well, there's no problem. People call it, people just call it anything. So far, you understand what they are saying. Now, one assumption, let's now continue. One assumption of the linear model is that the relationship between predictor and outcome is linear. For some of us that were around for linear regression, one assumption of linear regression is that the relationship between the exposure and outcome is linear. Both the outcome and the exposure, even though the outcome is usually linear, even if the exposure is categorical, there's a way you code it, you still believe that relationship is linear. You still believe. So, but that one does not work with logistic because the outcome is categorical. So for you to be able to now use the same principle to now predict that linear model to predict the categorical outcome now, you need a link function. You need to transform to form a link function. And there are options. We have options like probit, complementary log, or logit, which is the one that is used for logistic regression, logit transformation. So we are going to look at the meaning of this logit transformation. And when you do the logit transformation, is the logit that is the link function, because that's the one that make it behave as if it's a linear model. Who is making that? Okay. There's no question. We'll continue. If you have a question, please, you can ask. Don't hesitate. This is not general class. This is the workshop. So if anything is not clear, I like something from first principle. To me, if you don't move too fast and you understand all the steps, it's more important to me than you just rush everything and people are still blank. No, it's not. I don't like that. So that is why if there's any question, you can ask. So this slide is trying to compare the linear model and the logistic regression. The linear regression, logistic. You can see from the graph. You can see from the graph that the linear is a straight line. You will see something. One, the linear is on a straight line. You can see. You see another thing. Along that line, you can take any value. You will see the logistic home is not straight. It's one S shape like this. And all of them, they are consistent on 2 points. It's either 0 or 1. The value is either 0 or 1. There's nothing in between 0 and 1. But for the linear, along the line, you see value anywhere. And that's naturally how it's supposed to be. But this one, because the outcome has collapsed into 2, yes or no. And that yes means 1, no means 0. Even when a value is in between them, it will jump. They will now use 0.5 as the cutoff. Anything above 0.5, you count it as 1. Anything below 0.5, count it as 0. So can you see now? So it's all or none. Number one, you will see that another thing is that the line now, any value, you can still go beyond the line if you can continue drawing the line. If you have more value, the line will be going up. But this one is not like that. It cannot go above 1. It cannot go below 0. So that is the drawback of, because it's categorical yes or no. So even no matter your exposure, if let's say your exposure now maybe this one now is a cardiovascular disease we are talking about, they're positive or negative, yeah or no, and we are seeing maybe obesity in BMI, not obesity. Now we are talking of BMI. We are even talking of a blood sugar. We are talking of many cholesterol level. Think of many quantities something. You know they can assume any value, no matter any value they assume. this thing will come and say you either have it or not. It doesn't give that variation. Unlike if it is linear now, if it is maybe what you are measuring now is a particular maybe blood pressure now, blood sugar versus blood pressure. As the blood sugar increase, what happened to the blood pressure? As the blood sugar increase by then, the blood pressure reduce or increase. So you can look at it like that. It will follow this line, but because this one it has been into two, there, not there. No matter what change, the way, no matter the type of variation you have in your exposure, it doesn't make any difference here. The only two, you have two options, whether it's there or it's not there. It's 1 or 0. So variability in the outcome, in the exposure, may not mean much to the outcome. So in order to solve that problem, if you have the mental picture of this, you can depict two things here, three things. You see that, number one, the relationship is not a linear one. Then number two, the value are concentrated in two places. And even up to 40. Number four, there is no, you cannot have any value in between the two. Any value in between to collapse into either any of the two ends. And you cannot go beyond that 1 or 0. So you see a lot of limitations with it. And that is why intelligent people now came. Okay, this one is still saying the same thing. Intelligent people now came, what shall we do? What is the solution to this problem? So what I've already said now, the value from 0 to 1. So in this one, it can exist 0. This one can exist anything if it's the linear something. It can exist, but this one cannot exist. So what do we do? The logic, that's why we now come to what we call odds. Intelligent people now say, okay, this problem we are having is because we are dealing with probability. We are dealing with risk. Because the binomial distribution is probability now, is there. That is certain, it's 1. It's not there, it's 0. So it's like between 0 and 100. Or you use 0 and 1. You know, probability is either you use 1 or 100. So if you say 50% means 0.5. So that is probability. So the outcome comes in probability. And the intelligent people now came. What should we do? Okay, let's explore a method. Let's change that probability to the odds. You remember, for some of you that were around for the measure of association, I've also discussed this logistic regression in the lecture. Then even yesterday also we still talk about some of those things, concepts. Odds. What does odd mean? Odds, since probability is between 0 and 1, is limited between 0 and 1. Odds is not limited like that. It has its own problem. Let's first of all look at the difference between two of them to really know how people, the intelligent people now go to log odds. You know, risk is the probability that a particular event occur. Risk is the same thing as probability. So the relationship between risk and odds is such a way that if you have probability of an event happening, the probability of the event not happening is 1 minus the probability that it happened. And if you say the probability that it will rain tomorrow is 0.6, the probability that it will not rain tomorrow, it will be 0.4. Just remove 0.6 from 1 because they are complement. So odds is the probability of event happening over the probability of the event not happening. Prof, this is making noise. Do you hear me? So Dr. Yemi, you are mute your noise is coming from your hand. Mute your hand, please. You will see the odds is probability over 1 minus probability. That is probability of event happening over the probability of the event not happening. That is the odd of the event. You will see that, let's look at this table now. When probability is 0, the odd of the hair is 0 also. When probability is 0.5, can you see the odd is 1? Because you say 0. Odd will be 0.5 over 1 minus 0.5. That will be 0.5 all over 0.5. That will be 1. And when probability is 1, the odd is infinity. Are you see? So the implication of it is that while the range of value of probability is from 0 to 1, the range of value of odd is from 0 to infinity. So odd has a wider range. No, one of the problems I want to solve in that regression issue is for us to have a wider. I want them to go beyond that 0 and 1. I want them to have leverage to move, to vary the value very well. So it appears that odd is better than probability in that sense, because at least probability is from 0 to 1, odd is from 0 to infinity. You will see. Can you see? When probability travel halfway of its own way, odd has doubled the journey of probability. Like when probability is 0.5, odd has become 1. When probability now completed all the way you need to go, the odds go to the space, has gone to infinity. So that is why you see the way scientists reason. That's why can't we use odd? But that is no problem. So look at the relationship between the odd and probability now. You plot odd here, you plot probability. Because probability is from 0, it's on the horizontal now, as you see. It's from 0 to 1. The scale is from 0 to 1. The odd is from 0 to infinity. This 50 is just for convenience. It's to infinity, can be higher than that. Now, when you look at the graph now, when the probability is 0.5, odd is 1. And you see between this 0 and 5, 1. When probability now is close to its destination, 1, this one is going to infinity. It will just be going, it will not touch that one, it will just be continuing to infinity. And you see, you will see that the graph is not symmetrical. The half of this guy is not the same than the other half, because when probability travel is way, halfway, odd doubles. So if it's finished another way, if let's say you even double again, no problem, or even tetraple, but it has gone to infinity. So the first half of the journey for the odd is not the same thing with the second half of the journey. Whatever for probability, the first half of the journey is the same thing as the second half of the journey. But for the odd, apart from the fact that it has traveled faster than the probability, the second half of the journey, it has escaped, it has gone haywire. So it's not symmetrical. For you to understand it better, you see the next slide. Can you see? Even look at this first plot here. Is the probability, because even the probability also, if you take sample many times, it will follow normal distribution. Even binomial follow normal distribution. You know, we talk about it under inferential statistics when we talk about sampling distribution. So if you take sample many a time, even something that does not follow normal distribution may follow. Like for example, this binomial, the other yes or no, that is what we are looking at. If you take sample, it follow normal distribution. That's what you can see here now, the proportion. Look at it now. We know that halfway is in between. The middle of the graph is the halfway, and the probability is from 0 to 1. Can you see? Limit is 0 and 1. Then the middle is the halfway, 0.5. When you are looking at frequency. So that is why if you're trying to, if something that have binomial distribution, if you know, take sample many times, it will follow normal distribution, because the 50-50 will come up when you have taken sample many times, and that is why you have seen this graph. Then look at this, the odd you have changed to now, you try to transform to, look at the so. You pick here, look at the way. Of course, this 30 they put here is just for convenience. It's not 30, so it's infinity from, if you start from 0, it's going to infinity like that. Look at it. The graph is not symmetrical. It doesn't follow normal distribution. So it has its own problem. So in trying to adopt odd now, the skilled, the intelligent people still go for that. They say, okay, what do we do? Let's change the scale. So if they change the scale, let's now calculate the logarithm of that hod. If you change the hod from normal scale to logarithm scale, what it will do, it will now follow normal distribution. Look at it. Because log of 1 is 0. Logarithm of 1 is 0. Logarithm of anything less than 1 is negative. Logarithm of anything more than 1 is positive. You remember, for the probability, the halfway, the middle of the journey is 0.5. And the corresponding odd is 1. But that's 0.5. So when you transform that, or you find the logarithm, that halfway for the probability, which is 1 for logarithm, will become 0 for log odd. And anything that is less than that halfway will be negative. And anything that will be more than halfway will be positive. But negative to infinity, positive to infinity. For the logarithm of odd, the range of value is from negative side to infinity, no end. From positive side to infinity, no end. It's now symmetrical. And that is what we now use, is the link function, log odd, not the odd, log odd. Is there any question? Is there any question on what we have just described? Is it well understood? So no question. Dr. Balogun has not joined. So no question from any quarter. Dr. Ogungbe, you wanted to ask question? You're muted. Okay. All people are around. If you're around, say hi. Because some people just on their DC and the left. If you're around, say hi. Unmute and say hi. If you are there.
Hi.
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 Only
Hi.
Hi.
Okay.
Hi.
Richard is around.
Yeah, I know Prof is around. I know I'm seeing Prof now.
Hi.
I'm seeing Prof and Dr. Isaac. Yeah. Okay, I can hear that you are around. So it's well understood.
I'm also here.
Okay, that's great. So you can shout anyway. You can shout if you have questions. You can raise your hand and shout. Let's proceed. So that is just the logic. So odd is probability over 1 minus probability. And we have already told the logic behind that. And I think, now, in writing our regression equation, you know, if you remember, in trying to predict the value, because what you are looking for in regression is you are predicting the value of the outcome from predictor. You want to know the predictor that are responsible for a particular outcome. In that case, you write an equation. The equation is the outcome will be on the right side. The predictor will be on the outcome will be on the left side of the equation. The predictor will be on the right side of the equation. And that's it. That is why, if it is linear regression, you just say y is equal to, if it's linear regression, say y, what is this, you know? Yes, sometimes, maybe I don't need to expand it. Let me see.
It's okay.
Yes, I want to. Let me see if it will rise right here. Yeah, why is it not right? Okay, don't worry. At least y is equal to, well, you can call it b0, that's alpha 0 plus p 1 x 1. This is for this is for simple linear regression. Simple. For multiple, you say b y is equal to B0 plus B1 X1 plus B2 X2 and continue as many B and up to Bn Xn, up to as many as possible. This is for multiple. But because here what you are predicting here is first time is probability P. You want to predict, you want to have something like this. Plus now this P, probability of Y instead of the value of Y, it is not possible for you to follow linear. And that's why it actually, when you have calculated your, or you now say odd, you know, the remembering, your odd is probability over 1 minus probability. That is your odd. And it's not just the odd, the natural logarithm of the odd. Ln, natural logarithm of this is the one that is B beta 0 plus B1 X1. So this is the link. The link function is the logarithm of odd. It's called logit. That logarithm of odd is called logit. So what you have here is logit on this side that is representing your outcome variable. But this exposure variable is still the same, just like the way it is in linear. But you, to make this one assume linear function, you now change it to, this is what called the link function, which is a logit for the logistic regression. Yes, somebody is asking a question. Somebody have a question? Does anybody have a question? I thought somebody was talking. So that is the question you can see here. So don't mind, the alpha here is the same thing as the B0, you know. You can call it alpha, but when we are writing it also, we call it B0, which is the intercept. The B0 or the alpha is the intercept. If you plot a straight line, for the benefit of those who are, because I don't want to assume too much, if you plot a straight line, the intercept, this is the B0, where the line join y-axis, this line cross y-axis. That is the value of x, the value of y when x is equal to 0. Look at it here. This is the B0, which is the intercept. The slope of the graph is the B1. No, the y dx, the change in y divided by change in x, the x. That is the slope. So slope, which is B1, is equal to B1 is equal to change in y divided by change in x. So these are the two things that define the relationship. Yes. So YB is the value of y when x is equal to, it means that if x is not there, y still has value. Yes, number one, it means that it's not that s alone that is determinant of y. We say cardiovascular disease, obesity. It's not obesity that determines somebody has heart disease. Even if the person is not obese, he may still have heart disease. Are we following? Even person that is not obese. So that is what the usefulness of that thing. That what will be the value of y? What will be the value of exposure when the outcome of interest? What is the value of the outcome when the exposure, that exposure of it is not there? When S is not there, when S is 0, yes, that Y has something. That is the intercept. So the second one is change in Y per unit change in S. That is, if X change now, or for anybody that is obese, so what will it add to the cardiovascular disease? Yes, I'm now. Change in Y per unit change in S. That is the slope. So those are the two things. If you look at that equation, those are the two things in that equation, because those are the things that the relationship between S and Y, that's what those are the things that define it. And it's the same thing in the linear regression. It's the same thing. The only thing that we just look for now is the logic transformation and make it to function like that. That's all. Somebody is making noise. Prof, you are the only one that is on. Sorry, I don't know why the network just.
Network.
Yes, just went out, but I'm back. So let's proceed. Now, the same thing. Now, maybe I should not bother with better. I've talked about, look at this one now, multiple. When it is now multiple, the example you just first saw in the first slide is simple, but when it is multiple, look at this also. The same log hard. I don't know what is wrong with this internet. So the same, you see it, the same thing. The only thing I want to see one expression.
Right, we're not seeing.
Is anybody ask? Does anybody ask?
Sir, you need to share your slides, so we're not seeing this.
Oh, I will not share. Okay, sorry.
Yes, sir, we're not seeing your slides.
But you can see the slide now.
Yes.
So now you will see this one. What this one is just showing is that after you have
the slide is not showing up.
But somebody say he's seen it now. Who cannot see this slide?
Yes, it says come up. It's come up. It's come up now. It's come up now.
Okay. So what I was just saying is that after you have transformed you have done the logic, because the answer is giving you is that your result, the interpretation of result will be cumbersome somehow. Okay, what I wrote has gone. That's particular. Okay, let me just go back to now. This thing, okay, the same thing here. This alpha B0 and BY, you see, the BY, the regression coefficient, will tell you, what does it tell you? Is change in logic of Y. Change in the logic of Y per unit change in X. So can you see now? The interpretation is not like linear regression. It's not perfectly like linear, because linear regression will say change in Y per unit change in X. But here is not the Y. What is represented is the logic of Y. Change in the logic of Y per unit change in X. It's just like somebody you are supposed to go for a meeting, very important meeting, and you now send somebody. You send your daughter to go and when they now begin to say, okay, and they want donation, how many? The doctor cannot take that decision. You cannot take that decision. I say, me, I need to call my mommy or my daddy. I need to call to ask. There are some decisions you cannot take on our own because it's representing somebody. So it's the same thing. Here in linear regression, beta is change in Y per unit change in X. Change in outcome variable per unit change in S variable. Then in logistics, it's change in logic of Y per unit change in X. So for you, it doesn't make sense. And that's why intelligent people, okay, let's go back to where we are coming from. After all, we did log transformation, natural logarithm. Let's do anti-log. So when you now do anti-log, which is the exponential, that's what you are seeing here. Exponential, there is no anti-log is opposite of logarithm. You now calculate the anti-log of your result. So it will now come, it's change in Y, change in log. Who is making noise? I don't. Dr. Bako. you know, is changed in logit y per unit change in hertz. So when you now calculate the anti-log of it, if you remember, change in log, so that shows that there is a more like a ratio per unit change in hertz. So when you now calculate the anti-log now, it's telling you how many times the people that are exposed to that factor will have the outcome attribute than the people that are not exposed. That is the odds ratio. It's odd ratio. So when you change, when you calculate the when you have calculated your whatever you have calculated, then if you the beta, which is the logit of y, change in y, logit of y by unit change in hertz, when you change into anti-log exponential, it gives you the odds ratio. So let's see, before we go and run it, let's see the way you want to solve it with hand. But it's quite interesting. It will sound quite interesting to you. How do we? There's one aspect I don't want to bother you much about. Maybe I just say something about it before we now solve it. Is how do we, if you remember, people that were there when we did linear regression, how do we know the value? How do we fit? So we are going to calculate the value of beta 0 and beta 1 now. But how do you, if let's say you want to fit the value, how does it happen? How do you calculate it? How do you fit the value? If you pictorially, you remember the people that were in linear regression, we use method of least square. That line, try to see, to minimize the distance between the error and the line. That method is, but here, it doesn't use that. It uses maximum likelihood estimation. The maximum likelihood estimation is a very funny thing to understand, but you can understand it. Is what it means that it will fix a value, arbitrary value for is just by iteration. That is, making effort to try to know the best. You arrange in many ways. We will fix arbitrary value of B0 and B1. And for that arbitrary value, and see, try to calculate the probability of any of the vascular exposure leading to the outcome. It will try different value until it will now choose the one that give you the maximum value. That's what they call the maximum likely estimation. If you are to be hand, we need to solve that type of problem. We have to be rearranging data, and begin to calculate different scenarios and now choose the best. But thank God for computer. The computer will arrange it because it's very fast with the speed of light. Within 1 minute or even 30 seconds, it can rearrange it 20 times for you and come out with the result, or 50 times. And I will show you when you are running it in a computer, how you even set how many times you want it to try. But if you make it higher, it may be slow because it will be making effort to rearrange that number of times before it give you the answer. So it's more like trying to rearrange things. Now, what it does is that, what happens is that anyone, by the time you fix the value of the B0 and B1, anybody when you try to calculate for each subject, try to calculate the probability of a particular value being in B1 or B0. You know the outcome is either 1 or 0. Any value that the probability is 0.5, it above 0.5, it make it as 1. For anything 0.5 to 1, it will be 1. Anything less than 0.5 will be 0. That is the way it does it. And let's try now, let's make our, evaluating logistic model. I don't want to talk much about that. Let's just quickly make effort. May come and talk about it later. Let's just try and calculate something. Because last week when we were discussing it, I discovered that it was taking too long time. And some of the, to me, it's more like information overload. There is something that I shared the slide with you. You can go through want to know further about it. Yes, for the sake of this workshop, I want you to have the snapshot of understanding and how to calculate it. So from the formula, we just look at the formula for the simple logistic regression and look at an example of obesity and cardiovascular disease. What we used yesterday, the same example we used yesterday. We are going to use it for the simple logistic. Then there's another file we use for multiple, maybe by tomorrow. That one, the Titanic file, we use for multiple. Now, let's look at this table. I want to, because it's interaction, I want you to voice, people talk. How many, what is the sample size? What is the sample size? You can mute yourself and talk. What is
It's
it?
1,000.
It's 1,000.
1,000.
Yes. How many?
1,000.
Yes. How many people are obese?
106.
106.
They are obese? That is
300.
300.
300.
Yes, that's why it's a workshop. That's why it's good. Because sometimes if you
Oh, this
is
is
low,
300.
just
Wait,
yeah, it's 300.
300, sorry.
wait,
Yes.
let me see. Wait. Obesity. I'm seeing. Yes.
It's on the roll.
300.
So what about
Good.
the
300.
54?
Okay.
Diagonally.
Okay, cardiovascular disease.
Cardiovascular is called.
Okay, stop. Let's stop. I want
Okay,
to say
so
something.
obesity.
Okay, let's stop first. You know, by
Raw
convention,
total.
you know,
Raw
yes,
total.
yes, wait, Prof.
Raw total for yes is 300.
Wait, Prof.
Okay, so all 300 are obese, but out of this, the 300, only 46 had cardiovascular disease.
Yes. Then how many are not obese? How many are not obese?
700.
700, yes. And out of the 700, how many have cardiovascular disease?
60.
60.
Yeah, that's great. Now, totally, overall, how many people have cardiovascular disease?
894.
No,
106.
No,
106. 106.
106 have cardiovascular disease. Then how many do you have cardiovascular disease?
894.
894. That's great. So the same logic we want to use now. At least we have understood that by convention, the outcome is along the column, along the vertical. Cardiovascular disease is the outcome. So that is why you arrange it along the yes, no, along the vertical. The exposure is usually along the factors along the horizontal.
Row.
Or along the row. Thank you. So now let's look at, we already said that even when there is no X, forget about obesity. You can predict how many people have can't you predict without obesity there? Can't you predict how many people have cardiovascular disease? How many? If without obesity, how many people have cardiovascular disease?
60.
Somebody, the person that is talking, Prof, your speaker is not good. Just stop talking. Your speaker is not good. We are not hearing you. May rather
60.
Is it 60? Without, okay. No, okay, I understand what you are saying. We are not saying, without considering obesity as a factor. Forget about obesity. We are not saying that among the non-obese. Because I know when you say 60, you are talking of people with obesity, no. There's obesity, yes. For you to say you have obesity, no. There's obesity, yes. Without considering obesity as a factor, including obesity in your analysis, how many have cardiovascular disease? Okay,
106.
106, yes. Somebody is
You can calculate B0.
We are listening to you. We talk now. Who is saying hello? Ask your
I
question.
didn't get your question. I thought you didn't even hear me. I was even trying to. I wanted to follow the thread of the conversation. The
Yes,
last
your
question you asked.
it was your next call because when you were talking, it was doing blah, 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 blah. Okay, I said
Okay.
if obesity is not there as a factor at all, you can still predict cardiovascular disease. How many people have cardiovascular disease? Even forget obesity is a factor. Obesity, let's say, is not even a factor we are considering. How many people have cardiovascular disease? You know why I'm raising this observation? Because I'm trying to look for the best way for you to understand this logistic regression. It's not just about presenting something. Me, I learned because that session last week, I don't like it because to me, it was overloaded with too much stuff. And there's a tendency for people not to understand. So that is why I want to make it more interactive.
Thank you.
Yes.
Okay, so whether we consider whether we consider CVD or not, 106 people will still have obesity. I mean,
Thank you,
still
sir.
obese.
That's a prof talking. See, whether obesity is there or not, 106 people have cardiovascular disease. Even your data, you can summarize. If you didn't even take any that type of obesity, you get to know that in your data set 106 have cardiovascular disease. The correlate, the corresponding thing in linear regression is mean when you are calculating mean. Yes, I mean now. The mean is the crude. Even when you want to predict something, even without bringing in factors, the outcome you can calculate the average. The average, if you are talking of maybe is it blood sugar or blood pressure or whatever, hemoglobin concentration, you can calculate your average. If you remember, some of you that were in linear regression, if you remember when we were trying to look at how fit the model is, we said that the mean is the crudest model. For y, the mean of y, if you remember. You remember. So, why I'm asking this question is that the first thing we want to first of all look at is that, because when you want to run it now, I'm going to show you. SPSL will bring the result out. They call it block 0. Block 0 means that it has not considered the exposure variable. It's only the outcome is considered. It will give you the model. You get the picture now. So for y without x, look at my first something. We want to use this formula now. We want to use and. For y without x, you can see the log. If you want to calculate the logit, you know the log. You know, yesterday I demonstrated it. P all over 1 minus p is 100,984. Because if you want to write, okay, you know what? There's no. Just wait. See, this thing is writing. Okay, what I 100,894 over 1,000. Okay, let me just show you what I wanted to explain here. You know, if you are to say, you know, the people that have this is 106, and people that didn't have is 894, right?
894.
94.
So the log is 106 over 894.
Yeah, making 1,000. The total is 1,000. That's the sample size. You know, the probability that somebody have it would be, you know, sometimes it's good to start with first principle. P probability would be 106.
Well, we're not seeing any slide though.
It's not slide. I'm writing on. I think I share it now.
Okay.
I'm writing. Can't you see what I'm writing? I'm writing on the whiteboard. Can somebody see?
No.
Yes, it's visible, sir. We can see
Yes,
it.
we can see. We can see your board.
Prof said he didn't see it. I'm right. Look at it now.
Okay.
Can you see it?
Now we can see it now.
So 106 have cardiovascular disease. 894 did not have. The total is 1,000.
Okay. Yes.
The probability of having cardiovascular disease is 106 over 1,000. Is that not so?
Yeah.
The logit, the log. Let's talk about log before the logit. The log, the odds of having the cardiovascular disease will be 106 over 1,000, which is the
over
probability.
894.
Wait, I want to call for everything divided by 894, 894 over 1,000. I think you understand now. The upper one is the probability of having it. The other one is the probability of not having it. You know, the probability of having over not probability of not having is the odds. So with this type of thing now, all you need, this one would be 106 over 1,000 times. When you change that, it will be 1,000
over 894.
over 894. So eventually,
So 1,000 will cancel out.
Exactly. This one will cancel out. This cancel this. So the thing will be 106 over 894. 894. Do you know why I just did this? When you just say, okay, the odds is 10 over 894, people just confused. I just looking as if it's magic. But that just you must just need to just know that. So yeah, the odd is 106 over 894. So the logarithm of this odd now.
Natural logarithm.
Yes. If you divide this over this and calculate and check with your Lagrange, if it give you this minus 2.13227. And you know that when you put it here, you know that here, because S is not there. So this B1X, S will be 0. In this S in this formula is not there because we say Y without X. X is not there, it's absent. So the value will be 0. So in this case now, B0 times B1 is 0 times B1. The X is 0 here now. Times B1, it will be 0. So it will be B0. So this one is telling you the intercept. That is the value of Y when S is not there at all. This is the base, more like a baseline. This is more like the mean. Are we following? Is there any question concerning this? Now, if you remember, when you even summarize your data, when you do your univariate analysis, you don't even look at association between it. You just summarize your quantitative variable using quantitative data, using mean, and you could summarize the qualitative using percentage, proportion, which is for a probability. It's the same probability, we just find the log odd, the logarithm. We just find the logic of this value. So what we are just depicting here is the percentage proportion that have cardiovascular disease. This is the log odd. So this, like intercept, this one is serving like the mean. Like in linear regression, that will be the intercept, the value when X is not there. Are we together? And that means usually horizontal. If you remember, if you have to plot the graph, you know, sometimes the linear regression is just the answer. You know, sometimes many people, when you didn't attend a linear regression something, you make life this. Imagine now you have a scatter graph like this. You have for linear regression like this. You have something like this. This is Y. This is X. I want to draw the same thing here. If you see the same thing, I just want to depict two things on the same graph. It's the same something. If you look at it, this is the mean of Y, a value here. The mean value will just be like this. It will be horizontal. But the logistic line will be like this. It will cross the Y somewhere at angle. Can you see? The difference is these two. This is the regression line. This is the mean line. Yes, I'm not. So even in the mean line, where the mean cross Y, that is the mean of the value. That is the, even without considering X, that is the predictor it can give itself, the prediction it can give itself. Whereas this is so I'm drawing this one for you to understand the next thing. So this is like a, you can say this is intercept, this mean intercept. And when you are not even considering any x, but here you are considering this is the model. This is the intercept with the model here. There are two types of intercept here. This one is the regression intercept. This is the intercept for the mean. You understand now? Try to, if you look at it now, if you look at it, we discussed this in linear regression. Which line is closer to the value averagely? Is it the mean line or regression line that is closest to the values averagely? Which one is closest? Is closer rather. Is it the mean line or the regression line that is closer to the values, to those dots?
It's a regression line.
It's the regression. Somebody say mean line. It's the regression line. It's the regression line. If you look at it, because if you look at it, the regression, the way the scatter plot is moving, the line want to, even though it has not captured, all of them are not on the line, but the line is along. But this one just horizontal. Look at, some maybe look close, but the average distance from it is farther. Yes, it's farther. So if you look at it, you know that this line is more accurate. It's predicting it more than this. Now, let's go back to our slide. So what we have just done now is we have just looked at the value of y when s is not even a factor. We don't even use it as a factor. So what we have here now is like, why do we use this? We use this, the total number, the prevalence of cardiovascular disease, just like the way you look at the mean of quantitative variable. Now let's move to the next step. Now we want to look at the value of, we want to put x inside now. Of course, there are two possible values of x here. The obesity can be yes or no. So we want to start. Obesity is no. If it's no, the x to CB is 0. So what is the, how many people have the attribute? How many people have the attribute? Have the cardiovascular disease? When obesity is no. I want you to be responding, please.
60.
60.
60 from that table now. 60.
Yeah, 60. Can
you see? Total of 700.
Yes, yes, 60. So the log, the odd will be 60 over 640. You know, into the, you don't need to be going through the process. It's 60 over 700 by 6 over 40 over 700. Eventually, it will be 60 over 4 and 640. So you calculate the log of it to give you this. Of course, here, because x is 0, so this one also is 0. We cancel out this one. So it gives us the value of intercept. The intercept now, where s is there, the intercept is this, minus 2.361. This is the intercept when x is not even a factor. But when x is a factor, this is the intercept. When s is a factor, if x is the value of x is 0, this is the intercept. Can you see the difference?
Okay, I see.
Yeah.
So if you correlate it with what the thing I just draw here, I draw here. The first intercept with this, you are not considering s as a factor. You can't. I'm just trying to use linear regression for you to understand. If you are not considering s as a factor, the intercept will be the line that the mean cross, where the value of mean on y. Then if you are considering s now, but even when s is a factor, whenever s is 0, this is the value of y. This is the intercept. Can you see? So this is the first one we calculated. This is the second one we just calculated now.
Because x is there now.
Yes. But s is there, but when x is 0, x can be a factor, but it can be a 0. The value, when the value is 0, what is the value of y? Now, when for obesity, sorry, this thing is for obesity, sorry. This is for obesity is equal to 1.
1.
Yes, is yes now.
Yes.
So what is the value of what proportion have, how many people have cardiovascular disease?
46.
46. The people that don't have it, 254. Can you see now? So the log, the odd is this. The log odd, which is natural logarithm. When you calculate it, it gives you this. And you know that this the value of x is 1 here. Can you see? When you do it now, so this one is for both of them, BO plus BS. Because you have already known the value of B0 here, you will substitute here. When you substitute, you move this one, so B1 will be 0.658. Are we together? Now,
very well.
Yeah. So if you calculate this beta and beta 0 when x is not there, beta 0 when x is 0, and beta 0 when beta 1. When you look at it, you calculate their anti-logarithm exponential, it give you this. Actually, if you divide by when you just divide 106 over this, it just give you this. Can you see now? It give you this. No, this is the value. This is the odd ratio. So then that's for block 1 from 0. For block 1, that is when x is there now. The intercept, this is the odd ratio. Then for B1, this is the odd ratio. This is the odd ratio that is of x now. That is when one person is for everybody that is obese. The people that are obese, they are 1.93 times more likely to have cardiovascular disease than people that are not obese.
Wait, I can't see that last line.
Is it hidden? It's not showing. Okay, don't worry.
I can't see it.
Don't worry. I don't know why is it not. I will. Don't worry. I will. Can you see it now? Oh, let me share it again. Okay, let me share it.
Oh, it was better.
Yes, can you see now? It's the same data we used yesterday. If you remember, the crude odd ratio is 1.93. It's the same data. Remember? So let's run it. Let's run it so that we can see, because this slide is what I want you to see very well, and I want us to. You may ask me, how did I calculate this one? You can use for log. You can use your calculator or can use your Excel. It's Excel I used to generate it. 106 over D1, you can just calculate the log and anti-log. It's Excel. So I don't think. Okay. Let somebody share. Who will share for us? Who shared the data yesterday so that who will share? Nobody will share for us. Jane, will you share? Why are people silent?
I'm trying to open it.
Why is it that it's Prof that we share?
Trying to open.
Okay.
I made every effort.
Can I share, sir?
But I couldn't get through.
Share. If it's share, don't share Fatima. Okay. Have I allowed? Check you have not allowed yet. You are allowed to share now. That's great. That's great. Yes, can we see it?
Yeah.
Yeah, everybody can see it.
Yeah.
Yes. Go to analyze now. Go to analyze. Go to regression. Under correlates, you see. Come down, you see regression. Yes. No correlate to regression, yes. Then not correlate, regression, yeah, we're there now. Regression, click. Not correlate, regression. Yes. So go to binary logistic. That's number 5 there. Binary logistic, non-linear. Binary, yes. So the dependent variable is CVD logistic. No, I've coded them. So CVD, the last variable, yes. That's dependent variable. So covariate, obeys logistic. Obeys. Great. Then click on options. You will see, what I want you to click on, you see confidence CL for exponential B, confidence interval, click on it. Click on it, click on that box, yes. Yeah, because if you don't do that, it will give you the odd ratio, it will not give you the confidence interval. You will see, before you close, you see classification cutoff, you see 0.5 by default. What it's telling you is that, so whatever, any probability, 0.5 on the, I'm talking of the one on the right side. Any probability 5 and above, you will take it as 1. Anything below that, you take it as 0. You see maximum iteration. That's what it's telling you is that the maximum number of times you will try to give value B0, you will set different value B0, B1, and try to calculate the probability for many a time and then give the best value. And you see, so his computer, if you were to be hand now, you have to be, arranging. But the computer is a program. It just does it. So, and just click on continue. Continue. Okay. Yes, you share the output. Stop sharing and I share the output. Stop sharing this and I share the result. Because what you are seeing now, we are not seeing the result. We're only seeing the Dr. Fatih, maybe your network is slow. You stop sharing and I share the output for us.
It's not going out.
Yeah. Okay, it's coming. Yes, let's start from the yes, great. You will see the first thing.
Up.
Yeah, no, it's okay.
Scroll up.
No, it's okay, sir. It's okay. Let's start with it. That one is not a
dependent variable.
Yes, yeah. We want to start with that block 0. Let's see block O, beginning block. Can we see? It's a block O. That was the first thing we did. It's okay. So that block O is the one, if you look at it, what do you see on the table there? You see the logistic, the
Step
CVD.
1.
Yes. Step 1. It will tell you variable not in the equation, obesity. Can you see? It remove obese from the equation. It only does this one. Look at the variable in the equation down in this variable in the equation. You will see the beta constant for step 0 minus 2.13. Is it not what we calculated? Was it not what we calculated?
Yes, it is.
I want you to respond. That was what we calculated when we say y when x is without x. Can you see? And the antilog with the exponential we did is 0.119. Can you see?
Variable not.
Yes. So that is the first one. It's like when it's calculating the mean this thing for you. Okay, let's go down now. Let's go down. Let's go to block 1.
No, go down a little.
Yeah.
Yeah.
Yes. You will see the first one, test of model coefficient. Coefficient here, if you look at it, is trying to look at how good is the model. Something I want you to do. Okay, Dr. Fatima, before we go for that, just go to analyze here where you are now. Go to analyze. I want us to do cross tabulation, ordinary cross tabulation chi-square for both. Go to descriptive statistic. Go to descriptive statistic and cross tab. I want to do it for the chi-square for obesity. Just use that one. Use row, put obese. Want to do cross tabulation for the, you will see something. Do obese. Thank you. Then go to statistics. Click on chi-square. That's all. Continue. And okay. The result will be the last one down at the hand. That's the result. Can you see? This is result of what you do. You will see people following. Are people following? Other people are doing following. Yes. You will see.
Yes,
yes, that's great. You will see log linear. You will see likelihood ratio chi-square. Can you see the value? What is the value there? Likelihood ratio chi-square.
8.559.
9.559. 9.559, and the p-value is 0.02002, right?
Yes.
Scroll up. Yes. Now, Dr. Fatima, scroll up. Go to where you were the other time. Let's go scroll up. So go and meet the result we left behind. That table I was showing you. We see that it is the same. No, it's not this. Just it's okay. It's okay. Can you see? Omnibus test of model coefficient. Can you see what is the value? It's not 9.559, and the p is not the same thing.
559.
Yeah.
It's the same.
He just want to. He just try to test. He just try to test if that X has made improvement. That is, we are coming from block 0. Block 0 is that without X, so this is what the prediction you can know. That is the prevalence of the disease. That's the only prediction you can have about the disease. You are not brought in. What are the factors? So when you now brought in factors as obesity now, what improvement? Has it made any improvement in predicting obesity? Yes, because if it has not made improvement, the chi-square will not be significant. You will imagine
predicting CVD, not obesity.
What do you say, sir?
Predicting CVD, not obesity.
Oh, sorry, predicting CVD from obesity. Yeah, from obesity. So predicting CVD from obesity. Thank you, sir. So it means that because it's significant, it means that the model is good, has made tremendous improvement. That's the interpretation. You know why I'm trying to do that? And when you do linear regression, also we ask diamonds or tables that you try to interpret. Okay, let's look at this model summary. This one, they are just funny thing. They want to be like want to do like linear regression, but it's difficult to interpret. They are difficult to interpret. Like this one, likelihood. Though the logic being is the same logic, this chi-square is doing the same thing. But what I want you to look at here is cos snare arrow square, nege kereke arrow square, nege kereke arrow square. So this one they call them pseudo arrow square. Pseudo just means that something like it is not the real something. You remember what R square does? We calculate from linear regression. We calculate R square for. There are 3 ways you can even calculate it for. You can regression correlation, square of correlation. Then you can use the sum of square model over sum of square total. So you can also predict the value of y over observed value of y. Those are different ways to calculate this R square. In disability, it's not as straightforward like that. You cannot do that because it's not actually a linear relationship. It's way that they're just trying to model, use a link function. So many people just use different formula, and different people have different. There are two that this SPSS show. There we have more than two. That's the R square that people do. But look at it. This one is telling you that is 10, 0.01. I mean 1%, 1 to 1.9%. This one 1%. This is 9% of the. Yes, 1.9% of the outcome can be the variation in the outcome can be due to the exposure, but it doesn't make meaning here. So let's go down. Let's go down to. Let's go down. Classification table, yes. You see a table, classification table. So this classification table is trying to tell you, okay, how many you see, predicted, observed. Is trying to see what proportion of the thing that is predicted. So here now, overall, it's 89.4. So sometimes when we use here, you can use sensitivity, you calculate sensitivity and specificity to know how good this model is. Let's just leave that one now. Let's look at the last table.
So where did you get your 89.4 from?
Look at the table now. Overall percentage, 89.4. Can you see?
Yes, I've seen it.
So, because this one say the observed no, 894. The predicted no, 894 is 100%. Then the observed yes and predicted yes, the observed yes is 102. The predicted yes is 0. Can you see? So for this one now, the normal percentage predicted is 100%, is 0% there.
Where are you reading from?
Classification table. Classification table. This is one that is.
Okay.
The second to the last table you are seeing, classification table. So this one, it tries to compare the observed value and predicted value. What percentage of observed is predicted? That's what this channel is becoming unstable. Now, the first one for no, if you look at it, the no logistic and the no CVD. The no CVD.
Why is the disparity between the
what?
Can you hear me at all?
Sir, yes, I can hear you, sir.
Why is the disparity between the disparity between Cox and Snell R? That one is just under 0.1. Why is this side so high, 89.4? Why is so large disparity in one study? You can't hear me.
I hear what you said, but you are talking of R. Is it the R?
The Cox and Snell.
Cox and Snell.
Cox and Snell.
Yes, 0.1.
While the overall percentage predicted is 89.4. So why is the disparity so wide like that?
I already told you that they should discard it. Those people are just making, it's not useful here. People are just making effort to, this thing, the principle is from linear regression. People are making effort. And these people that, if you run another software now, you may not see cost now, maybe another thing they put there. People just advise the people that do SPSS, they are business people. For their own, the statistician to advise them to put anything here. So it's not useful for any
So that means we should ignore it.
You ignore it. I'm just telling you it. Exactly.
Okay.
In fact, I just decided to use it for people that were around last week. If you look at the modality of the presentation is a little bit different now. Because I felt that the presentation of last week was too voluminous about what the two months. And sometimes some of them they are more theoretical. So that is why some of those things I'm saying here, they are on the slide also. I just keep them but I just want to explain them here, make more meaning, practical, the examiner. And you see that from this slide, you discover that there are too many things in even logistic than in linear. The reason is very simple, because it's not as accurate, it's an adaptation. So people come with different ways to try to look at the model. But whereas the linear is more straightforward, you don't need 1, 2, 3 things. You have look at the how model is good and you move ahead. But here, people predict different things just to explain the model. Some of them also are abstract. Now, here, this classification table is the same table if you want to do specificity and sensitivity and specificity, and even plot ROC. You can do that here. They will not do that. I will not even dabble into that unless I first of all take the class on diagnosis test, because that's very straightforward. Yes. So you remember when we came to Bayelsa, we did it now. So I've done it in Port Harcourt, so some of my trade. So it's so interesting. So until you do that one, because me, I don't like talking to the ear, things that don't have meaning. But I like being systematic. So that sensitivity and specificity can be done here also, but we leave it for that diagnosis test. But what I'm just saying here is that no, can you see? 100 observed say no, and logistic and the predicted no. That's why it's 100% predicted here. But here is 0, because the yes here, under the yes is no, is 0. So the 0 is not, he didn't predict. How many of these did he predict? 0. So when you now overall, everything is 1,000. Out of this one, how many is able to predict very well? It's 894 over 1,000. That's the 89.4. This 894 over 1,000 that give you 89.4. That is able to predict correctly. Now, the last table, the most important table, even sometimes you don't even need all this other one. It's just for you to enhance your understanding. Your results you are bringing out are on this table. You see the beta. You see the constant that the B0 for when X is there, we calculated minus 2.367. That's what if you remember, that's what we got. Then this is the one for B beta 1. B1 is 0.658. This is what we got. So what the interpretation of this one is not like that of the linear regression, where you just say that, oh, this is the regression coefficient. You say for per unit increase in X, this is increase in Y. But what you are seeing is 0.658 mean per unit increase in Y in X. This is increase in log odd of Y. Can you see the log odd of the probability of having log? Let's just say log odd of Y. So it doesn't make meaning. So until you convert it to the odd ratio, you now calculate the antilog, which is exponential. This is antilog 1.93. So what it's telling you is that the people that are obese are 1.93 times more likely to have cardiovascular disease. This is the confidence interval. Is this significant, Dr. Ogunge? Dr. Ogungbe, is this significant? Is Dr. Ogungbe there?
Significant.
Yes. Why did you say that?
It's between 1.28 to 2.91.
So it does not cross 1. So it does not contain 1 in the range. Yeah, 1 is not in the range. That's great. Who is making noise? Somebody is making noise. Any question? Somebody is making noise. Please mute your Dr. Ogungbe, mute. Once you answer question, you mute, okay? Now, yes. Now, look at the p-value is significant. So you see that if it's significant with the confidence interval, it will be significant with p-value. But why? You know that if it is last time you want to publish, and they don't want you to even put p-value, they are okay with the odd ratio and confidence interval because you can know if it's significant there. So the confidence interval give 3 information. P-value give only 1 information. And that information P-value give is part of the 3 confidence interval give. So there's no point if you do in our research. In our research, we put both P-value and confidence interval. And it's tautology. The reason we do that is that we know that the examiner will not see it from that light. So the examiner can even decide to fail somebody before you come for the exam if you didn't put the P-value there. So that's why you put the P-value there and put the confidence interval. But it's tautology. Yes. Yeah, I'm listening.
There's something you said yesterday. You said confidence interval is inferential statistics. Why p-value is what? There was something you said that p-value.
Oh, you didn't get me. So that's why it's better to be not to be informed than to be half informed. So it's better to hear something very well and be clear. It's good that you have asked now. Rather than you go and say, because you can go and say somewhere and say, yes, we were in a training and so said this. So the person has said, no. So if somebody told me that somebody said that, I will know that maybe you didn't hear the person very well. Now, it's just like when Yetunde says somebody told him something. Yeah, I mean, I don't believe that because he didn't understand why he will not say that. There are some things that even no person will even make that mistake. You may not hear very well. What I said is that hypothesis testing is a form of inferential statistics. Confidence interval is another. They are separate method. Confidence interval and hypothesis testing, they are separate method of inferential method. They are separate inferential method. In fact, there is a third one where that is Bayesian method. Can you see? We have Bayesian method.
So
we are talking about pre and post probability, post-test probability, pre and post-test probability.
So there is Bayesian.
There is Bayesian by Bayes theory, yes, Bayesian method.
There's hypothesis testing, and there's what's the third one?
Bayesian method. We have hypothesis testing, confidence interval, Bayesian method. 3 of them. Hypothesis
and all these
they are
inferential
method. They are inferential method. They are inferential method. They are inferential method. That is inferential statistics. Inferential method. So hypothesis testing. So it's hypothesis testing that ends with p-value. Yes, I mean, either t-test, chi-square, ANOVA. Think of any form of test you do. You end up with p-value. That is hypothesis testing. Hypothesis testing. P-value is the final judgment. The confidence interval is a separate method. But you may see that sometimes it is a programming that people program it together. People that have like SPSS now. When you do t-test, it puts confidence interval of the difference between me and them. It doesn't mean that confidence interval difference between me has nothing to do with t-test. It's a separate thing. They just bring it together, program it together so that when you run it together. Do you get it now?
Yes, sir. So because the statement I made was that you said that confidence interval is an inferential statistic. So are you saying that it is not?
Well, are you sleeping? I said confidence interval is an inferential method. Hypothesis testing is an inferential method. They are separate method of inferential statistics. Even I say that there is Bayesian method, which is another one that we don't normally use it. And it has been there for long, but people don't use it. So the commonest one that people use is either hypothesis testing or confidence interval. So what I'm saying is when you see we run analysis like this now, it bring p-value out, it also bring confidence interval out. Now, this p-value is this word statistic that is generating this p-value. You will see also, if you look at the odd ratio and likelihood ratio chi-square, it's the same p-value that gives you 0.02. It's the same thing, showing you it's the same thing. The word statistic is 0.02. Like look at the p-value for the one hop here, which is the chi-square for likelihood omnibus test, which I say is the same thing as the likelihood ratio. It's the same p-value. And this was statistic. I will explain this was statistic now. So that is the hypothesis testing in this in the what we are running. The odd ratio and confidence that is a separate thing. It's another method. Do you get the picture now? So when you are presenting your result, normally you don't need to even present the two because you are saying the same thing. And since the confidence interval give more information.
That's what
Hello? Is everybody
that
stop?
was what I wanted to ask, because some people present the two in one study. Some people present both confidence interval and the p-value.
And there's a reason for that.
So since there
Your distance is low, you can't hear you. Are we following? Your distance is low. Even the Ugo that is talking, even our resources, both of them we presented. Because there's a reason I've explained the reason you do that. But Dr. Ikobo, we can't hear you. Can't hear you again. Maybe your network.
there are studies, many studies where people put p-value and confidence interval when they are reporting the same thing. So
Yeah, that's what.
So is it right like that, or when you use one, you don't need to put the other one?
If I'm an editor of a journal, I will. If you put confidence interval, you don't need to put p-value. You don't even need the two. The confidence are giving more information. I would prefer the confidence interval. Lancet will not take that p-value from anybody. They don't take it. So they prefer the confidence interval. Now look at okay, Ugo. What is it there?
Network.
So as he was asking the question, I said that in your study, is it not both of them that are there?
Yes, sir.
The reason is very simple, Dr. Ikobo. The reason we present both is that the examiner may not know. So if the examiner does not know, you just put your confidence interval, because if you have to choose one, you choose the one that has confidence interval, odd ratio confidence interval. I should know if it's significant or not. Whereas the p-value is telling you if it's significant or not. But if the examiner does not know, the examiner is looking for p-value, didn't see, he has already failed the person. No matter what you say, you say that no, you don't need that. The person will even say, where were you born? Where were you born? So if you in this business, you pass. When you pass, you cannot have your this. You cannot become authority on your own. Like me also, when I was doing my, even I knew I had to put the p-value. So every time they ask, I say yes sir, yes sir. Yeah, the reason I put this one. Yes sir, yes sir. You're right sir. You're right sir. But sometimes the way you are talking, even the examiner can know that he doesn't know what he's saying. But of course, if you show that you are fake, so you don't need. They will say that the boy is so arrogant. So arrogant, can you see? So arrogant. So that is what. So it's the environment. So even in reviewer also, if you present to the, if you want to publish, if the reviewer say this is what I want, and you want to publish, you put it like that. Unless you want to go to another journal. So that's just it. So life is is a marketplace. Everybody has his own opinion and everything. So that's just it. So
okay.
Yes. Why did you go to the last one? Go up, see Dr. Fatime. Dr. Fatime, go up.
Fatima.
Fatime. It's not Fatima. Maybe she should call it.
Fatime.
Dr. Fatime, what is the right pronunciation? Because it's
Fatime on
let her talk now. What is the right pronunciation? It's not there.
It's not here.
It's there. It's there. Is it not the one scrolling? Is there? He didn't want to answer you. Dr. Fatih?
Sir?
I said, what's the Prof is asking, what's the right pronunciation of the name? It's not Fatima.
How do you pronounce your name?
It's Fatme.
Fatme.
Eh?
Yes, sir.
Fatme. Who is talking? Somebody is making noise on the ground. Okay. Yes. Let's see. Go back to that table. Variable in equation. Let me explain. No, down. No, down. In that block 1, the one we're explaining, it's not this one. You are in block 0. Block 1 is still down. Yes, this one. Yes, okay. Now it's okay. It's okay. It's okay. This one. Look at this table. You see, this is beta.
For that.
What's that, Prof? Any question? No. This beta you are seeing is 0.658. Now, this was statistic because it's one of the statistics to see how good is the significant, if the model has made significant improvement, if X has improved the prediction of Y. So standard error, if you divide beta over standard error, you know what standard error means? Standard error is a measure of how precise your estimate is. Know this beta. Is there any question? This beta you are seeing is a statistic. It's trying to predict parameter, which is the beta in the population. So if the standard error is very small, it means that the beta you are B you are seeing here. I don't like it. This B you are seeing here is close to population parameter. If the standard error is very big, it means that the beta is far. So if this was statistic we are seeing, you divide is by profile. So this was statistic we are seeing. When you divide the beta by the standard error, it follows normal. The worst stat is worst statistic, but is the way each software present that differ. If you are using a pinfo, I wouldn't know if it's the same thing with startup. If you are using a pinfo, is Z as it will give you. That worst statistic is Z, and that Z, you know, Z means something that follows normal distribution. So beta all over standard error follow normal distribution, but if you square it, it gives you a chi-square distribution. What we have now is beta all over standard error square, which is what they call word here. But the same thing in EpiInfo is Z. If you remember when we were discussing chi-square, the origin of chi-square, the first person to describe chi-square, Carl Pearson, described it from squaring standard normal deviate by squaring normal distribution. That's how he discovered chi-square. Can you see now? So B all over standard error follow normal distribution. If you square it, it follow chi-square distribution. The word you are seeing here is a chi-square distribution. There is some software, it is the Z they put there, they don't square it. But of course, you get the same, the p-value they give you is the same. So that's why if you are running some software, you see Z here. Here you see chi-square. It's the same thing. Just a matter of squaring the Z, it gives you the chi-square distribution. Now,
you took
what did you say?
No, I just remembered when you took us on chi-square, you talked about the different types of chi-square. It's not that it's making sense.
Okay.
Remember, you know the different types of chi-square. Yes. Okay.
Yes.
You know,
so when we talk about the origin, how the chi-square came, I said that if you square standard normal deviate, normal distribution, it become chi-square. The first person to describe it, that was what he did, Capexon, that he did to get that. So I think we understood that. So in your research, what do you show? Just show the P odd ratio and confidence interval. So, or you show the odd ratio and the confidence interval. But sometimes people may like to show beta or this one. You know why it is good? If I'm examining, I would like you to show it. You know why it is good? Some people tell lie a lot. Some people can change odd ratio and they want it to be bigger. They want it to maybe significant and change this confidence down, just change something. But they will not know that all this beta, zero, they have something. So if somebody change the value of odd ratio for you and now change something that is significant, whatever. If you have beta there, all you need to calculate the antilog. If you calculate the antilog, it's not the same thing with the ratio that the person has told lie. Do you get it now? Because you can try it now. Go and calculate the antilog of this. It will give you 1.932. That's just it. So if you remember the constant also, the antilog we calculated for it is this. But of course, that one is not useful in your result. What is useful is for the X. So you can stop, Dr. Fatima, you can stop sharing. You can stop sharing. Any other question?
There's a question, sir.
Okay, go on. Okay.
Now, how can we really give effects to the table? Because there are quite a lot of information. So what exactly the interpretation of the table?
Interpretation of the table. Maybe something, because even as you are even talking now, something is drumming in your place. Maybe those drum has been disturbing you. Because I just finished explaining that this last table, that is where the result you bring out. All those other things are just explanation. This last table. So if I run this one now, what I bring out is t-test. Okay, let me show result. Dr. Iguilo. Dr. Iguilo. Dr. Iguilo. Is it there? Unmute yourself and talk. Dr. Iguilo. Okay. Okay, here today. Hello? Here today? Okay, don't worry. Let me show an example. Good evening. Good evening. Okay, can I show your research the logistic aspect so that I can see?
No problem, sir.
Let me show you.
I can learn too.
Dr. Ogungo, let me show you the way we put it on the table. Let me show you an example of research so that you see. So, yeah. Let me just quickly bring the something now. Project. How did I save your result? 1 minute there. So can you see? Can people see? I'm showing the Word document. Can you see? Can other people, because probably is last to see it. Can another person see?
Yes, we can see.
Yes. Prof, have you seen it now? Hello? Okay. This is the Word document. If you look at it, can you see Dr.
Yeah.
So here, we have two groups here. This person did comparative
Table
study,
4.
right? Yeah, table 40. This person did comparative study, right? And in the comparative study, he has two groups. They call some people supported group, some people not supported group. So if you look at it now, there are two results here. Look at for this age now as a variable. The linear regression, logistic regression is on overall quality of life. You know, that quality of life, that particular thing you are regressing on the table, you will not see it on the table apart from the title. What you are going to see on the table are the factors you are regressing on that thing. It's only that title that will show. So multiple binary logistic regression of overall quality of life on associated factor. Age is a factor, but with the age is only for this supported group. For the unsupported group, there is no age there. So if there are only one group now, this table will not be in two parts. If you will not see something like supported, just see p-value, odds ratio, confidence interval. That's all. Because it's a comparative study, we have two parts. That's why we put it to two. You see the same thing, p-value, odds ratio, confidence interval, and confidence interval. So you see the p-value, the odds ratio. So look at marital age. Yes, you will ask. Don't worry, tomorrow, and tomorrow we'll run something, you will see continuous variable also. If you look at it now, if you are running logistic regression, I've already said it, it is the outcome that is categorical. The exposure can be anything. It can be continuous, it can be categorical. Like age now is a continuous variable. We didn't put it into category when we are running it. We just running like that. Can you see now? So the interpretation of the software when you run it like that is that for per unit increase, as age increased by 1 unit by 1 year, so the odds of having good quality of life, overall quality of life, will be 0.99 increase. Okay, let's go to this. Look at the next one, marital status. The marital status was not applicable on the supported group, it's applicable on the non-supported group. What this one is, you see that we now put under the odds ratio, we put 1 under not, because there are two values of marital status, currently married and not currently married. We have divided them into two. Currently married, not currently married. The currently married is the one that, not currently married is the one that was coded 0. The currently married is the one that is coded 1. So we are going to talk about that. Okay, maybe another thing I will have explained even from the beginning before we run, when Dr. Fatima opened that thing, is the coding. Yes, I mean now. So, you know, in logistic regression or any categorical variable you want to use for regression, not only logistic, you must create a dummy. Though tomorrow we'll talk about much about that dummy. You create a dummy. It's either 1 or 0. So for this marital status now, currently married, we coded 1, not currently married 0. So that not currently married, which is the reference, we now put the odds ratio will be 1. Because if you say that people that are not currently married, how many times go to likely to have a more quality of life than the people that are not currently married? Itself, it will be 1 now. Because if you are comparing yourself with yourself, it's 1. Then this currently married, you are comparing it with not currently married. And that is why the odds ratio is 1.67. It's telling you that the people that are currently married, they are 1.67 times more likely to have good quality of life than the people that are not currently married. Look at education. You know, you have a lot to learn here. Look at education, and is part of this one. We look at it tomorrow also. It's part of what we do tomorrow. Look at education. The education also, we have categories. It's not a quantitative variable. There is an ordinal variable in the sense that It's a variable that is in hierarchy. 1 to 4 mean no formal education. 1 means no formal education. 2 means primary education. 3 means secondary education. 4 means tertiary education. That's what you see there. So we just code them like that and run it. So, and it's significant. You can see what this one is telling you is that as you move from one level to the other, if you are in secondary, you have secondary education, you are 2.4 times more likely to have good quality of life than the person that is primary education. If you have primary education, you are 2.4 times more likely to have good quality of life than the person that has no education. If you have tertiary education, you are 2.4 times more likely to have quality of life than the person that is secondary education. That is the interpretation. And the confidence interval, because it does not include one, is significant. The same thing on this side also. Can you see? 1.94. Another thing I need to say. Okay. Question?
So for this ordinal now, what test did you use?
This odd.
That's for this education, this increasing, because it's it's ordinal.
Yes. Which test did I use?
Yes, sir.
We did the regression. The logistic.
Okay.
Last week, if you remember last week, when we this Tatani we are going to do tomorrow. This one we are going to run tomorrow for multiple.
Okay.
Data on Tatani. If you remember,
yes,
there's socio-economic class, there's class there, which we now use rank 1, 2, 3. Instead of education, if you want to create dummy for this, because there are 4 classes, you want to have 3 dummies. And you now run it just in your useless thing, you just wait. So forward variable become 3 in your hand. If you run like that, it's look up and you have to put all of them at the same time. And I explained the reason. Tomorrow you're going to see, because we demonstrated it last week. The reason you have to put all of them, if you create 3 dummy for one variable, you must put all of them at the same time. If you don't put it, it's something else you are doing. You are doing it one by one. It's something else you are doing. I'm going to demonstrate that. So in this one, it makes sense. The only problem we usually have is if the categorical variable is not ordinal. Do you get it, picture now? If the categorical variable is not ordinal, you don't have option. But you have to create those. But you still have option. The option you do is that you can look for one that is separate from all of them. Maybe if you look at, since it's not even ordinal, it's just like if we do ethnicity now, you now see knowledge of something, you now see that maybe the Hausa has higher knowledge compared with the rest. The percentage that have the knowledge of that thing is higher, is similarly higher, is in Hausa than all the rest. You cannot compare Hausa with the rest. You make it 2. Do you get the picture now? You now compare, or maybe a particular category is lower, extremely lower than the rest. You can compare it with the rest. I don't know if you understand me now. So rather than, it makes more sense than creating those useless 4 dummies at the same time, or 3 dummies. So if you cannot help it, you may have to do that, but those are the way out. But when it is ordinal, it makes sense. You just use the order. If it is continuous variable, you use it like that. That's the beauty. That's the beauty of the. But if it is
sorry, sir. Excuse me, sir. So I can see from here, it means that like age and education now, they don't have any reference category. They were just entered.
Yes, now there is no reference category because age is a continuous variable. You just use it like that. The other one is ordinary variable. You let it that you code them 1, 2 to the other one 1, 2, 3, 4. You give them order. You order them like that. Does it make sense?
Yeah.
Well, the education, okay, I understand for the age, but for the education, why don't we have?
How do you discuss it? How do you discuss it?
Right. Well, it was this discussion that you gave, the explanation you gave now. But looking at it now, I can see that in reference to other compared to others, like employment.
Something that you have submitted.
I have to defend what I have my work now. I'm just looking in retrospect that okay, education, occupation now. I can see that they don't have a reference category at all. It's just like, despite that they are in classes.
And there's a linear relationship there.
Unlike employment status.
And there's the linear is that as the educational class is a class, it's an ordinary variable. You understand now? It's going up. The number 2, 3, 4. The highest is 5. You understand now? So if you remember, I don't know if it is your work, the way the person, maybe it's your own, the way the person coded it. In fact, the number 1 was the professional. So the last one, your skill is coded 5. But for me to run it, I have to reverse the code it for me to run it. You understand me now? So that the lowest is number 1, the highest is number 5. I don't know if you understand me now. Because if you don't do that, your interpretation will be different. You understand me now? Your interpretation will be different. This education now, what it means, one mean, as you see, maybe you can work, maybe in a place you can put it better in your research. The way you arrange it, the lowest is 1. 1 to 4 mean there are 4 ordinal categories. 1 to 5 mean there are 5 categories ordinal. Does it make sense? Yes, I'm now. 1 to 5, 1, 2, 3, 4, 5 mean that there are 5 categories. The other one, there are 4 categories.
So is there a reason why marital status for supported is empty? Is it because it was not significant?
Marital status. Okay.
That's under,
even the age is for not supported is empty now. The reason is that you only do the regression for the one that you have gotten some association, somehow. You don't waste your time doing multiple regression with something that is not associated. So those are the things that were significant for each different NDC. And we don't want to duplicate the table so that the table we can, at the snapshot, we'll have separate table for supported and not supported, because it's not all the time that it is the same variable that you are going to run on both sides. It's different variable. This thing you are seeing now, the multiple regression, they are run separately. The multiple regression for the supported is different from they are not run together. Even though we may command together, we split the file. Yes, I mean, they are separate regression. We don't put them on the table. So those ones that are relevant in each table, those are the ones you put for each one. I don't know if you understand now. So another thing I just want to say here, another way of presenting that this one employ, not employ now. Instead of what we can say employ stroke, not employ. Not employ. Yes, I mean now. And just put it like that. That's the best, but many people, they'll still be asking you, where is the reference? Where is the reference? Where is the reference? The standard is that when you say stroke something, that one will be the reference. But some people will still be asking. So that is why you put it to them old school, like this one. Put it separate line and put 1 there. I don't know if you understand me now. You put it in a separate line and put 1. Just 1, by putting 1 as the odd ratio, you are indicating that is the reference. That is the reference group. Does it make sense?
It does.
Yes, sir.
Dr. Ogungbe, does it make sense?
Yes, sir.
So, because a lot of, once you grasp this aspect, very simple, there's nothing. Forget about all those too much theoretical something. If you understand how to interpret it and how to run it, that last table, that's all. That's all. So you are home and dry, and your distance is significant. That's it. It is in fact, the issue there is that presentation of result and interpreting the linear regression is more difficult because it's more cumbersome. But this one is more straightforward. Even though it may be difficult to understand the logic behind it, it's more straightforward than linear regression. And whether you like it or not, that's what you will encounter, because in medical literature is logistic regression. That's the order of the day. So I think we can stop here. And I don't know if there's any question So by tomorrow we are going to run multiple.
Hello.
Yes.
I have a question.
Okay, no
I have
problem.
a question.
One after the other. Yes, go on.
I have a question, eh?
Yes, sir.
Can you hear me?
I can hear you. We can hear you.
Okay. With respect to age,
Yes,
with
sir.
respect to age as a variable there,
Yes.
if let's say it's not stratified into, let's say, above 50 and below 50, if it is just a continuous variable, how can it be used for regression? How would you create a dummy with that kind of this thing? Maybe explain, but I didn't get it.
Are you talking of the data we use or this result?
The age, yes, the age. Like this one now, it's not categorized, it's not stratified into above 50 and below 50 or this.
Yes.
So how do you create a dummy with this kind of?
No, there's no need for dummy. If you follow, if you have a follower, sir, you only create dummy for categorical variable when you want to use it for regression. And that's linear logistic. Is categorical variable that need, because what you're going to do is a thing of number. By nature, the continuous variable, quantitative variable that are number already, there's no problem. It's only the categorical variable that are non-number. You now create dummy for. I don't know if you understand me now. So age is a continuous variable. You don't create dummy for it. Even when we do our category,
okay.
You know, even before you assume, you decide to use age as a factor, you might have done your chi-square, and before you did the chi-square, you will have categorized the age into group now before you can do chi-square out.
Yes.
That's why you get to know, oh, age is significant, you want to put in regression. Even despite that, you run the age like that, because running the age like that is more accurate. Your category, let me tell you something, you may categorize your age and use it and say it's significant. Another person may categorize the same age in different way. It may not be significant. Yes, I mean, you can do age categorization, it will be significant. If you do it in another way, it may not be significant. So for the fact that it's significant categorization, because when you categorize, you lose a lot of value, you lose a lot of information. So that is why when you are running the regression, you run it like that. It's the one that gives you the real information.
Okay.
Okay.
Please, I have a question.
Can I ask a question, sir?
Okay. One after the other.
Yeah, please.
Yes, sir. My question is that
Who is talking? Wait, Dr. Ogungbe, wait. Prof, ask your question.
Sorry, sir, can I go ahead?
Dr. Ogungbe,
Okay.
wait.
Sorry, sir. I was saying that I didn't quite understand why you put you give reference to some, and in the others there was no reference group.
Okay. You know, I know what happened now. Maybe you, as we were talking, you step out to do something. You know, this trend that we are not showing our face. It's only Prof that is showing his face, and sometimes Dr. Kuba and Dr. Isaac. So we know what they are doing. Sir, I said that this age, the one we didn't put reference for, we use the value that it is not category. Age is not categorized. We run it like that. It's age as age in year. Maybe we should put in year there. Age in year, there's no category. So if there's no category, if there's no categorization, when you are running the regression, there's a quantitative variable used directly. So there's no need for reference. Then the other one, education, the one that are ordinal, like education and occupational class, those two, they are ordinal variable. You have already coded them, you rank them 1 to. So if there are 5 categories, you rank them 1 to 5. You run it like that also. There's no need for if you remember, you are around now when this Titanic something, the one we're going to do tomorrow. You know, there is this class 1 to 3. We created dummy. We also rank. We said that we use the dummy to run. We also use the ranking to run. So when you are doing a logistic regression, you can use the rank. But you don't use the rank if you are doing linear regression. If you want to include occupation or education in linear regression, you have to create dummy for it. You cannot use that rank because it will be giving fresh impression that the real value of that thing is 1, 2, 3, 4, 5, which is not the real value. Because in linear regression, we did exactly. But it is allowed to now create a dummy 1, 0, 1, 0, 1, 0. So if we are using, if we want to use a ordinary variable like education and occupation in linear regression as an exposure as a factor, you have to create dummy for it. But if it is logistic regression, you may not need, you may create, you may not need. It's better you use the ranking. Is it clear, sir?
Yes, sir. Yes, sir. Thank you very much.
Thank you, sir. Dr. Ogungwe, ask your question.
Sorry, I was looking forward to learn something. Probably we have not gotten there yet, or maybe I did not really spot it. In one of my studies, we had to compare day 1 and day 2 hemoglobin level of post-operative patients. So we now find out that one thing that will be a confounder is their fluid balance. Some of them have different patients with different amount of intravenous fluid and urine output. So we decide to control for fluid balance. And the way we did that was to do a linear regression, a logistic regression model to correct for fluid balance. So I don't know, is it applicable here? Is it another way of applying this to correct for a confounder?
Okay, I will. Don't worry. By tomorrow we'll be talking about correcting for confounder, because that's multiple regression that make you to correct for confounder. So we can actually even run one here, because what we did yesterday, this one we still have age here. You know, this is the data we even use yesterday. We use stratification, because maybe we will run it before we close. We will run it and I had age. That's how to correct. But in that your study, what is your outcome measure? What is your outcome variable? What is your dependent variable in that your study?
Okay, yes, we're trying to see the estimated blood loss as estimated by different professionals compared to what the actual blood loss is using a particular formula. So,
okay. What is your outcome measure? What is the if you want to do regression, now what is the variable that is the outcome? You say you did logistics.
What are you trying to?
You say you did logistics because you want to know blood loss, yes or no, or blood loss above certain level or no, or whatever. Blood loss above this and below or below this. What was the outcome measure? How did you measure the outcome?
What we're trying to do actually is to check whether there is a close agreement between the two methods of estimation.
Agreement is different from, you see,
that's diagnostics now.
Yeah, thank you. In fact, it's close to that, but agreement is different. Yes, I'm now.
We actually do Bland-Altman method for the agreement, but before we did the agreement, we decided to correct for fluid balance.
You see, the issue
because
is that
we felt that would be a confounder.
But the issue is that, okay, if you correct for the fluid balance, how does it affect? Because the agreement, when you are running the agreement, is different from when you are running regression. What I just want you to know, just want to actually know is that even when you are correcting for the confounder, the fluid loss, if you want to, you can use linear regression if it is amount of fluid loss directly you want to use. If you want to use logistic regression, there must be a cutoff. That's it, fluid loss above this layer, so above this one below. You divide it into two. That is the only way you can do logistic regression and say you are controlling for any confounder with the logistic regression. I don't know if you understand me now. Is it that you are trying to do the study, or you have already done the study? Have you finished the study, or you are just in the process of doing it?
Yes, in a way we have concluded it, but I can still add some inputs if I learn better.
You have not even answered me now. How did you say you did logistic regression? Unless if you want to share with us.
Yes. The dependent
you want to know how you express your
clear.
dependent variable. Because logistic, there must be two possible outcomes for the value of the outcome for logistic regression. You did.
This is actually the reason why I decided to join this workshop, because I actually gave it out to a statistician, and I don't think I have good understanding of what was done other than what I'm telling you now. So I felt okay, maybe if I
Can
join
you
this
share?
workshop, I'll
Okay,
learn better.
maybe can you share the result with us? Can you share the result? I just not that you send it to us. You can. I can allow you to share now. Just open your computer and show us the result. That's what we mean by sharing. Not that you are sending the result to us. I just allow you, just like the way Dr. Fatime share this thing. Can you share now? Oh, it's not ready.
I don't mind. I don't mind sending the result to you maybe after this workshop. Then we can talk about it.
Okay, no problem. You can send it. I will look at it, and if you need to open it tomorrow and look at it. So that's just it. So is that should like we're not you just got to know about it. If let's say you are around for our I'm coming for our linear regression, it will help you. But I want you to subscribe for the video so that the linear regression is there, so you can watch it.
I will definitely do that.
Do that. Because all these even video they are going there also.
I'll do that.
You can even do that to that so that you get it. You can say what you want to send to me. Somebody is asking another question.
Yes. Can you hear me?
Yes, I want to ask. Okay,
hold on. Okay, Prof.
Yeah, 3 questions at the same time. Yes. What I was saying, some clarification.
Okay.
In the likelihood estimation, the number of iterations by default in SPSS is 20.
20, yes.
But what I mean, is it possible for somebody to choose below or above that 20 that is the default?
If you look at it, you can choose. You can
choose.
Any
reasoning? Any reasoning? Yeah, that's any reasoning behind the number of iterations one would want to make.
Well, I can't give you an answer if there's any better.
Because the SPSS just gives you 20.
Yeah, if before they can give 20 also, I will find out the reason. Okay. It's all experts like you that will have advised them to give this thing. I don't know if the number of iterations should be proportional to the sample size or whatever. So I will find out. But I'm sure that whatever they are doing is experts like you also that give them advice. Yes, I'm now. I know that if it's longer, the thing will be slower also. The result will not come out on time. And if it is shorter, it will be faster. Because it's arrangement, with speed. Okay, any other one? You said that we have 3 questions.
Okay.
That's all right.
No. I said 3 people. People were asking.
Okay. Ugo, your question.
Yes,
Ugo, your question.
Can I go ahead, sir?
No, Ugo. No, hold on, Ugo, ask your question. Ugo.
Hello, sir. Can you hear me, sir?
I can hear you.
Hello, sir. I can hear you.
You said you have a question.
That, if you're asked to write, yes, sir. That's what I'm asking.
Go on.
I was saying that if you're asked to now write this as a statement, that's the way you write it under your result when you're writing it up. Like I just want to have an idea of how you write.
How do you interpret, right? How do you interpret, right?
Yeah, yes, exactly.
Okay, it's like I interpret for because this one is a today is a semi-lazy person, so he asked me to interpret something by one level among supporters.
Hey, your pardon, sir. Hey, sir. Okay, supposing the age is significant, interpret it. Age because it's not significant.
I interpreted one here. Look at it.
Interpret the age.
Okay. It's the same thing. As age increased by 1 unit, the likelihood of having a good quality of life increase so times. That's all. If you look at it now, as the level of ratio increased by 1 level, can you see now?
Yes, sir. But okay.
But if it is for the one, if it is if it's for the one like this one now, presence of medical condition, I would say those who have medical condition are 4, 5 times. Those who have medical condition are those who don't have medical condition, rather, if you look at the reference is yes here. The no is the one. Those who don't have who didn't have medical condition are 5 times, more likely to have good quality of life than those who have medical condition. And it could be as high as 10 times. I will now quote the health ratio and the 95% confidence interval. As high as 10 times.
10 times.
Look at it, the confidence interval, the upper limit is 9.59, which is 10. You can approximate to 10. Can you see?
Okay, so you have to include that statement that it could be as high as
you can.
9.
Yes, you make it robust. If you look at it, I think I put it here. Maybe I didn't. It could be as high as 4 times. Can you see now? It could be as high as 4 times. I will now quote the odds ratio and 95% confidence interval. When you are saying it, you put your DC, you can approximate. But when you are quoting your confidence interval, put the exact value that you have there that generates your statement. That's all. It's very straightforward to interpret. So the other one, if it is age continuous variable, as it increases by 1 unit, the likelihood. If it is ordinal, as it increased by 1 level, and you see the likelihood increased by 2 times, or 3 times. It's very straightforward. Dr. Ogungbe, I ask your question now. Welcome.
Yes, sir. Okay, when you said it could be as high as 4 times, that is the upper limit of the confidence interval, right?
Yes. Even some people even put lower limit. They say it could be as low as best. Well, they will even say it could be as low as they put the lower limit of confidence interval also. But you can put that as high as if you don't want to talk too much.
Okay, sir.
Yeah. Any other one? Any other one? Okay, I think we.
That's my question.
Okay, yes, ask your question.
Yes, just looking at this table that you're sharing now, you have two. You calculated the logistic regression for the 2 variables differently, for the supported and unsupported.
It's not 2 variables, there are 2 groups. The person did comparative study, there are 2 groups.
2 separate groups.
Yes.
Okay.
Because it's a comparative
Secondly,
study.
if you are to calculate the logistic, no, I understand that, sir. If you are to calculate the logistic regression for any data that we to use.
Okay, is that Dr. Babangana talking, right?
Can you hear me now, sir?
Yes, it's better now. It was breaking. Go on.
Yes, sir.
Go on. Go on, sir.
All right. Looking at the data we used initially, the data we use on cardiovascular obesity, sir.
Yes.
I noticed that you converted the cardiovascular also to 0 and 1.
Yes.
Even though that was the outcome dependent variable.
Yeah, that's dependent variable, yes.
Must you convert both the dependent and independent variable to 0, 1 for us to be able to run the logistic regression, sir?
Yes. Whenever, if I say something, anytime you are using a categorical variable to do regression, either linear or logistic, whether it is the outcome or exposure, you have to create a dummy, and dummy is 0 and 1. So we'll talk further about that dummy tomorrow, because we even demonstrate it, because when we're going to, the data on Titanic is on multiple.
No, I understand the dummy. I just want to be sure that you have to convert
the categorical. Anytime you are using categorical, unless, like for example now, if I'm doing logistic regression, that shows that the outcome is categorical. In that situation, my outcome will be 0 and 1. You understand now? That outcome variable will be coded 0 and 1 because I'm doing logistic regression. Now, the exposure variable, if it is continuous like age, I will not code it. I just use it like that. Any other variable that is categorical in the exposure, I will code it 0 and 1 also. Unless if that variable is ordinal, I can use, I may not code the 0 and 1 like this one, education. I will now give a rank 1 to 4. If there are 4 classes, I'll put 1 to 4. If there are 5 classes, I'll put 1 to, I don't know if you understand me now. That is the way to do it. So if that categorical variable.
No, I do understand the.
Did you understand?
How to create domain? I do that. Yes, sir. Very well, sir.
What is it?
Very well. Thank you, sir.
Are you talking to me or you are talking to someone else?
Hello, sir. Hello, sir.
Yes.
The network is poor.
I just had one thing. So based on what you were just explaining to him, so that means if, for example, this age now, if this age had been put in categories, the interpretation would be different.
Yeah, if let's say age is in category, let's say that some people they do funny thing. Even their data is already in category, even from the beginning. Like somebody sent to me now, it's already in category, they've already categorized it. So you don't even know the original value. So let's say we even put in 2 categories now. If there are 2 categories, I will not say, oh, those who are older than, maybe less than 20 years, they are 3 times more likely to have good quality of life. I will do it like the way you do for yes or no. Yes, I mean for those 2 categories. Exactly. If it's possible also, the age, the categories there, they are about 4. And in that case, you have to create 3 dummy. Make one as reference. When you make one as reference, you were here yesterday. Tomorrow we'll look at it, because if you remember the data of that tomorrow, we created dummy for the social class. The social class. So we create good dummy. You make one as reference. The one as you make as reference is the one you are going to say. If let's say I make age 1, the first age as reference, I now have 3 dummy. I will now say each of them, how many times are they more likely to have good quality of life? More than the first one. More than the first one, yeah, because that is the reference. I seen this question you are asking now. The data we are using on this thing. Okay, let's or should we stop here? This tonight, or should we run down, or maybe we'll run the first thing tomorrow? And this same data set, we also run the age with it, with this obesity, before we go to that Titanic. Yes, tomorrow we'll do that. Dr. Ogungbe, you were still asking one question, right?
No, for now, sir.
Okay, that's great. Tomorrow. So you can send what you want to send, so let me look at it.
All right, sir. Thank you.
Yes. So I will upload something also so that we can reduce the volume. Because it's already.
Thank you, sir.